Okay, let's finish this chapter today. So we are currently studying the least squares problem, where we cannot find the exact solution for a given linear system usually because we have more number of equations than the variables. Okay, and then so let's see. Okay, so we formulated our problem as this a kind of minimization problem, where we want to minimize the length of the vector b minus ax, or we want to minimize the distance between the two vectors, of this one and this one, right? So by carefully choosing our vector x, we want to minimize the difference between these two vectors. Okay, so that difference is defined by this norm. Okay, and then we want to find that x that will minimize this equation, and then we derived so this kind of equation where our error vector, which is this vertical vector, okay, that vertical vector should be perpendicular to each of our column vector in A, and thus we form the inner product by transposing each column vector as a row vector and then multiplying it on the left, and then we obtain this set of linear equations, right? And then altogether, the right part, these parts are all common, and then the left part has a different row vector, which is A1 transpose, A2 transpose, and so on, and thus entirely this guy will be changed into A transpose, which is our matrix. And so we form this matrix equation for our linear system, so that we can obtain this x hat, which minimizes this least square problem. Okay, then so let's see. So this equation can be rewritten in this form, right? By just distributing this multiplication, and then setting them into really equation, and then we obtain this. And then in case this A transpose A has a inverse, or that is an invertible matrix, and then the solution can be obtained as this. Okay, so we will discuss the case where A transpose A is not invertible shortly in a few slides later. But at a high level, I wanted to emphasize that even though we started with this minimization problem, the solution for that minimization problem is obtained as the solution of this equation. Okay, so we want to minimize something, and that solution is basically a solution of another equation. Okay, so at the last part of the last Tuesday's lecture, we discussed about this briefly. So this kind of minimization problem, the solution for that minimization problem is obtained as this equation. I mean, the solution for this equation, and that solution is obtained by just taking the derivative of our function to minimize, right? And then by setting them as 0, then the solution for this equation will satisfy this minimization problem. Okay, then so we want to minimize this, right? Back to this least squares problem, we want to minimize this, and then if we take the derivative of this guy and then setting them in as 0, and then that equation will be obtained as this. So let's derive this although yeah, it is not discussed in the book, but yep, I'd like to describe how we do the differentiation on this kind of complicated form. Okay, in order to do this differentiation or computing the derivative, I want to discuss about some of the vector calculus or matrix calculus. So we know how to derive how to compute the differentiation of maybe sine x, and then that will be cosine x, right? And then maybe log x. Of course, the base will be e, and then it will be 1 over x, right? So you guys know all these differentiation equations, right? And then I'd like to give you some function, a vector function. So for example, let's think of the function that maps this vector into some scalar. So let's talk about this function that has the domain as R2 and the codomain as R. Right? Two-dimensional vector is mapped into one-dimensional, the scalar value. Right? And then let's assume this function, this function f is defined as this. Okay, so this is basically a function that maps two-dimensional vector into, I just need to define the scalar, right? So, okay, so this is our function, right? Okay, so in this case, if we have this this kind of function, f, x1 and x2, and then how can we compute the differentiation on this function? We have the two variables, x1 and x2, right? And then our derivative by differentiating with respect to some variable given this function is done through considering only one variable at a time. So that way we consider this something called the partial derivative. Okay, so we want to differentiate this equation with respect to x1, but in this process we just consider all the other variables as a constant. Okay, as a constant. And then what is the differentiation of this? So it can be viewed, so this one is our variable and this one is also our variable, but x2 is not a variable. So in this case it's a 4x1, right? Because it was a minimum, it was computed into this derivative. Okay, and then what about this guy? This guy will become 0, right? Because that is considered as a constant at this moment. And then 5x will be, 5x1 will be just 5. Okay, and then what about the partial derivative with the x2 this time? And in this case, you can compute the partial derivative with respect to x2. So this one is the only variable that we have, and then it will be 6x2, right? And then just to make this problem more interesting, let me just add maybe this term x2. Okay, and then in this case, back to this partial derivative with respect to x1, then yeah, this guy is our variable. So what is the partial derivative with respect to x1 given this 4x1 x2? Can anyone tell me the partial derivative with respect to x1? So it's like this. So 4x2, this entire part is considered as a constant, and then times x1, right? And so it's like maybe 7x1. For example, if this guy was 7, and then it will be 7 after doing the differentiation, right? So this part will be our result of the differentiation, right? And so it will be 4x2, right? And then similarly, when doing when computing the derivative with respect to x2, okay, and then it will be obtained as 4x1, right? So far so good, right? Okay, and then the derivative of this function with respect to each individual variable by computing its partial derivative, and then we obtain these two, and then we can just form the vector, right? And then this kind of vector, right? So this vector is basically the collection of the partial derivative with respect to each individual variable, and then this vector is called the gradient. Okay, gradient. And so we can imagine, one kind of example of our function that maps the two-dimensional vector of x1 and x2 into another scalar value, right? So in this case, we have an x1 and x2 axis in the bottom, right? And then when x1 was 1 and x2 was maybe 2, and then this one will be corresponding input vector, and then we compute or we obtain the height of this function, or this kind of some kind of a mountain, and then the height of this corresponding value, and that will be our function value that is obtained as this guy, right? Because that is our function definition. Okay, and then the geometric meaning or interpretation of this gradient, okay, this gradient, which is the collection of a partial derivative, is that okay, at this point, and then we can think of some sectional kind of shape or function. So sectional means so at this point we just fix x2, and then x2 will be fixed as 2, right? And then it's like chopping this mountain vertically along this maybe this kind of knife that is along the this kind of line where x2 is fixed as 2. And then if we view that kind of curve from the side, and then we will obtain some one-dimensional function. And in that one-dimensional function, so let's imagine we just cut this mountain vertically, and then let's look at it from this side, okay? And then suppose that function is has the shape of this guy. Maybe this one is result of after cutting this mountain vertically, and then looking at this mountain from the left or from the side, and then suppose we are x1 is 1 here, and then at this point, we can think of this slope of this 접선이 영어로 뭐죠? Tangent line, right? So yeah, basically the derivative or differentiation will give you the slope of this tangential line like this, right? And so once we compute this guy, okay, the partial derivative with respect to first variable, that value will give you the slope at this point, right? And then of course, in order to obtain the slope value from this equation or this function, yeah, we do not only need this x1, right? But also we need an x2, right? So both of these variables, I mean the particular value of x1 and x2 are required or necessary to obtain the partial derivative with respect to x1. And then what is x2? Yeah. So we assumed, or we started from the x1 being 1, x2 being 2, right? So we can plug these two values into our partial differentiation, right? Partial derivative. And that way we can obtain the slope at this point. So that is the meaning of this partial derivative representation or expression. And then similarly, the second part, or this partial derivative with respect to the second variable x2, that has the same meaning. So at this point, okay, so at the 1, 2, and then we just previously we cut them through this line, and then we can also cut it through this line that is parallel, or that assumes the x1 as the value as x1, right? So in this case, we can cut it along this parallel line, and then that is still kind of vertical, right? But we cut them by fixing x1 as 1, and then we can view it, or we can view the mountain shape from this side, okay? That will also give another kind of a slope, right? And then at that moment, or that point, if we think of the slope of that curve, and then that curve will be this guy, okay? Okay, so if we think of our least squares problem like this, okay, so this is basically a function, right? So entire value of this guy is just a scalar, right? So this part is scalar, but what is the input? Input is the vector x. So it is basically the same situation where we have from our function, we have a vector x as our input, and then this whole part, yeah, even though it looks quite complicated, but after you compute it, given this b and a, then you will obtain the scalar value. So that is basically a scalar because we compute the norm of them. Okay, so this situation is quite similar to this kind of example. Okay, and then how can we minimize this representation? So let's call this as a star. Okay, and then how do we minimize this star with respect to x1 and x2 as our input vector? Okay, so in this case, how can we utilize this partial derivative that we obtained previously? So intuitively from this figure, so this one can be one example of our function that will give us a scalar given the vector input, two-dimensional vector input. And suppose our kind of, shape of our function looks like this. And then from here, what is the minimum point? Okay, what minimizes this function? So the function value is corresponding to this z-axis, right? And so if we can think of their height at each different point. So when having a point over here, then corresponding x1, x2, and then that will give us some height corresponding to this point. And then what is the minimum or lowest possible point? Lowest possible point will be over here. Right? Okay? It's just the same as like this. So if we have maybe this kind of curve, and then what is the minimum point? The minimum point will be this, right? And that minimum point will satisfy the equation of having zero slope, right? So at this point, the derivative will be 0, right? So similarly in this figure, so if we achieved or if we arrived at this point, if we think of this point, and then their kind of slope will be 0, right? Because that is not, there is no downhill from that point. Okay, so in this case, if we chop or if we cut this mountain at this point along the this axis and this axis, okay, and then both sectional curve, both curve, when cutting it like this and this, so those two different kinds of curves will have the zero gradient, so the zero slope at this point, right? So when cutting it at this way, and that curve will give us zero slope at this minimum point, and when cutting it through the this direction, then that curve, another curve given by that kind of cutting process will give you the zero slope. Okay. So our conclusion is that this guy should be 0. Okay. So because the slope for this mountain should be 0 and the slope for this mountain should be 0. And then suddenly minimizing this this function, okay? Minimizing this function is turning out to be the problem of the set of equations. So the first partial derivatives should be 0, and the second one should be also 0, right? And then that way we obtain multiple number of an equation, okay? So we want to find out x1 and x2 that both satisfies both equations. So far so good, right?
Right. So when we differentiate those given equations partially with those
x1 and x2.
Yeah. And so after we get those multiple equations, and how about the situation when the linear system is inconsistent? Is that possible?
Yeah, that is a very good question. So we basically obtain the set of equations. But what if what if our set of systems has no solutions at all? But in general, it will be guaranteed to have the solution. I cannot prove rigorously or mathematically at this point, but intuitively, how many equations do we have? Yeah, the number of equations will be the same as the number of variables, right? So we usually have the square kind of matrix shape. I mean, in case of the linear system, but this one is not a. Oh, this one is a linear system, right? What I mean by that is each equation is represented as a linear equation, right? But what if we had maybe, maybe 4x3, 4x cubed. And then in this case, if we take the derivative and then 12 times x squared, and that will be part of our derivative. And thus it will no longer be linear equations, right? But in this particular case, it will be a linear equation. So in this case, it will form the yeah, it will form the same number of equations as the number of variables, and usually we can find the solution, at least one solution, but we can find the multiple solutions in this point. What will be that solutions? I mean, what will be those solutions corresponding to? So at this point, so given this curve, I mean, this is just a one-dimensional function like fx equals maybe x squared, yeah, maybe this guy. And then by just taking the derivative and then setting it as 0, we will obtain the multiple solution. And what do those multiple solutions corresponding to? It will be like this point and so on, because these multiple different x values will have the slope as 0, right? Okay. So the reason why I give you this kind of example is that if we can compute the partial derivative with respect to each of our variable, and then forming it as a vector, and then setting it as 0 from this equation, okay, from this equation, and then that solution will basically minimize that point, because those points that has the 0 partial gradient for each individual variable, that point will have the slope as 0, yeah, at different sectional kind of mountain after cutting the mountain, yeah, in a different manner. Okay, and so the remaining part, okay, so the remaining part will be how to compute the derivative of this guy. Okay, how to compute the derivative of this guy. So we just make it as this guy. So the norm is positive. Okay, so the norm is positive, and so minimizing fx will be the same as, so more exactly, so the minimizer or the particular x value that will minimize fx will be the same as fx squared. I mean, in case fx is always positive or greater than or equal to 0, right? Because this one, yeah, is a positive one, and so if that is minimized, and then the squared value of it will also be minimized. So if it was so like this kind of table, x and fx, yeah, x was 2, 1, 2, 3, 4, and then the fx was 5, maybe 2, and 6, and then what is the minimizer? I mean, when x is 3, and then it will be minimized, right? And then what about the fx squared? And then 25, and then 4, and 36, and so still this x equals 3. I mean, that value is still a minimizer, right? So this guy is the same as this guy, right? Okay. So I'd like to make it as a squared, okay? And then this function, we want to compute the partial derivative of this function. And then how do we compute it? So this norm squared can be represented as this. Right? So the norm squared of a particular vector will be represented as the inner product with itself, right? And then, okay, so what about this guy? If we distribute this transpose, and then it will be x transpose and A transpose. You guys know that, right? So AB transpose will be B transpose A transpose, right? And also, what about this? It will be A transpose and B transpose. So plus sign doesn't get affected by the transpose, right? And then it can be just distributed, yeah, in a normal manner. And so the first one will be transposed as this part, and then B transpose, right? And then X AX minus B, right? Okay, and then let's just distribute or compute this guy, and then this guy times this, and then this guy times this, B transpose AX minus, and AX transpose A transpose B, and plus B transpose and B, right? So I just rewrote this equation. Okay, so let's think of the partial derivative. So x is our vector, right? X is our vector, and then we want to compute the derivative with respect to each of our individual variables, right? Okay, so in this case, if we can compute the partial derivatives of this guy and this guy and this guy, okay, that will be, if we just add them together after computing derivatives separately on each 3 different terms, and then if we add them up together, and then that will be our gradient. The collection of partial derivatives like this. And this guy, what about this guy? We don't need to care about this guy because this one is constant, right? B is the given constant, right? Okay, then let's focus on these 2 guys first. Okay, so these 2 guys first. Okay, so for this guy, B transpose A is what? So B transpose is like this, and then A is like this, and then it will form a single row vector, right? And then that row vector will be a constant vector determined by given B and A, and then this one is our x vector, right? This x vector. And then, okay, so maybe through some numbers of B transpose and A, and then suppose we obtained maybe 3 and 2. And our x variable would be x1 and x2. Okay. So we just focus on this guy. Okay. So in this guy, what is our function in this case? It is 3x1 plus 2x2, right? So in this case, what is our gradient? What is the partial gradient of this guy with respect to x1? Is 3. What about the partial gradient with respect to x2? 2, right? So this vector will be our dx1, this kind of vector, right? Okay, so if we had this term only in our function, and then this guy should be 0 and 0, right? Okay, but in this case, it is not even an equation, right? Because it doesn't involve x1 and x2. Oh, so in that case, the solution may not exist, right? Okay, so in general, solution may or may not exist. And this one is quite simple case where, so what if we have maybe y equals x plus 5, for example, in this maybe 2x plus 5. In this case, can we ever find any points that has the 0 slope? So we cannot find at all such a slope, such a value that has a 0 slope. So in that case, the derivative will be 2, and then that cannot be 0, regardless of any x values, right? Okay, so but anyways, we obtain the partial gradient at this point. We have this term, but we have some other terms, like this guy and that guy. Okay, and then how can we obtain this guy? 3 and 2. So this guy is basically the transpose of this guy. So this part will be this part, and that part is coming from this part, right? And so this row vector is B transpose A, and then that is simply transposed into a column vector. That is our gradient. Okay, so this guy's gradient, the transpose, which is A transpose B, that is our gradient. A transpose B. So in general, let's think of this case, y equals W transpose X. So in this case, W means some vector, maybe some constant vector, and then we have the column vector X. And then what is the gradient in this case? I mean, in general, yeah, if we generalize this kind of particular example, then the gradient in this case will be what? W. Because we want to transpose this guy into a column vector. And so this guy transposed will be our gradient. Okay. And then let's look at this guy. Let's look at this guy. X transpose and A transpose B. So that part can be represented as this. So this guy is X transpose. And this whole part, A transpose B, will be over here, right? And then can we write, or in this inner product, what is the, so in this inner product, this one holds true, right? So it means A transpose B equals B transpose A in case A and B are vectors. I mean, yeah. So in this inner product notations, we assume A and B are vectors, but the second equation is just a kind of an example of a matrix multiplication, right? And so in this case, A and B may be a matrix. So in that case, this one is not equal, right? But in case A and B are vectors, then this one is overall creating just a scalar value. And then, yeah, this guy and this guy will be the same. Okay?
So is the second equation correct?
Yeah, in case A and B are vectors. And then A is this vector and B is this vector. That is just generating the scalar value. So for example, 2 and 3, and maybe 4 and 5 is the same as 4 and 5 and maybe 2 and 3, right? Okay, so we can freely change the order between them. So between this inner product, between this guy and this guy, X transpose, and this vertical vector will be A transpose B, we can freely change the order between them, right? And so in this case, we change the order between them, but in this case, we basically transpose, yeah, apply the transpose on each part. So this guy is transpose, A transpose B transpose, and X transpose transpose. Yeah, so this guy will be the same. And what about this? This guy is B transpose and A. Right? Okay, so we obtain this part. And then what is the gradient? What is the gradient of this guy? This guy should be further transposed, right? Just like this. Okay, so in general, it can be represented as X transpose W, right? And then this W will be our gradient. Or this guy, after doing the transpose on this left-hand side as our constant vector, that will be our gradient. So this guy transposed will be our gradient, and thus A transpose B will be the gradient. Okay. Okay. So what we did so far was computing the gradient of this guy, which is A transpose B, and the gradient of this guy, okay, gradient of this guy is also A transpose B, right? So they are the same thing in this particular case. Okay, so we only have this part, okay, to compute the partial derivative. So that is the most tricky part, I think. But in this case, let me just consider this kind of function fx, which is our vector, and then x transpose and maybe b and x. So this guy is like this. X transpose is some vector and b is maybe 2 by 2 and x is over here. So this one is x transpose b and x. Okay. So in this particular case, how do we obtain the gradient of this guy? Okay. So it's like second order term. Okay, second order term. It's involving the multiplication between these x values and so on. So for example, if it was 1 and 1, what will be the result? x1 squared and x2 squared, right? And then what about 1, 1, 1 over here? So in this case, this part will be x1 plus x2 and x2. Okay, I mean, yeah, x2, which is our row vector, and x1 and x2, and then it will be x1 squared and yeah, so we basically multiply this guy with x1 and this guy is with x2, right? And so we additionally have x1, x2, this kind of term. Does it make sense? Okay, so basically this guy is a kind of second order term with respect to our variables. Okay, and then in this case, we can obtain the partial derivative, right? So in this particular case, what is the partial derivative with respect to x1? So 2x1 and x2, right? And then what about the partial derivative with respect to x2? We can obtain that, right? Compute that. Okay, but back to this general form. How can we obtain the derivative of this guy? So that is obtained by some kind of a convenient rule that we can apply here. So if you remember this guy, fx and gx, so what is the derivative of this guy? So we just, so from the, so if our function is the form of a product of multiple different functions of f and g and so on, we just, similar to computing the partial derivative, we just consider only one term, only one part as containing the x and the other part as just a constant. Okay, just a constant. So if we view this fx as our function that contains our variable, and then gx as not containing our variable, and treating it as a constant, and then it will be f prime times g, and then we take turns, right? And then we move on to the second part, and then f g prime. So you guys learned this from high school, right? 배웠죠 이건? But what? So if we extend it, and then what if we have an h here, and then it will be like this, right? Okay, and then using this, we can So you guys know the differentiation of this guy as 3x2, but we can still apply, we can obtain the partial derivative of this guy by using this rule. Okay, it's like x times x times x. So this one is fgh, right? And so this one is, so let's just assume that we only know dx over dx is 1. And then if we view this as only part that contains our variable, and the derivative of this guy with respect to x will be 1. And so we just multiply these two together, x and x. And then we just move on to the second one. Okay, so that is also giving us x times x plus x times x. So altogether 3x squared, right? So far so good, right? So even though I don't prove that this guy is still valid in the case of vector kind of spaces. So in this particular case, we can apply the same rule. So we have so we have these two parts that has the function, I mean the variable x. And so roughly we can maybe separate them into three parts, and then just viewing one at a time, as though that containing our variable. So let's view this guy as the part containing our variable, and then this part will be no longer considered as a variable, and thus this entire part. So this entire part will be considered as a constant, right? And then what is the derivative of this guy? So it is bx and y. So it is a kind of has a form of x transpose, and then some constant w, right? And then what is the gradient? I mean the list of a partial derivative. So that is this guy, right? So dx is something like this. Okay, and then let's move on to the second part of b. So b contains any of the x. So b is just a constant matrix. So if we compute the partial derivative, and then that will give us just a 0, right? So we can just safely skip that. And then let's move on to the last part. Okay, so in this particular case, we view this part as our constant part, and then this x part is our variable part, right? So that is corresponding to this guy, because we are considering the last part as that containing our variable. Okay, so we have some row vector over here, and then we know that this W transpose X will give us the list of partial derivatives as this W, which is a transpose version of the left vector. And so it is like X transpose B transpose, right? Okay, and then this guy will be B transpose X. And then we have Bx and B transpose, and so B plus B transpose and X. Right? That is our gradient. Okay? We just applied this rule. Okay? This rule, and then apply this product of these values. Okay, so keeping that in mind, we are now ready to compute the gradient of this guy. Okay, so X transpose A, and X, what is the gradient? So in this case, if we view this guy as our variable, and then this one, this part, so this guy is our B, right? And so the result will be A transpose AX is corresponding to this BX. And then what about the B transpose X? That is A transpose A and transpose and X, right? Okay, and then if we just transpose it, and then it will give us A transpose and A and X. So that is the same thing, right? And so if we add them together, it will be just 2 A transpose AX, right? We just applied this rule onto this particular shape. Okay, so we are almost done. So this guy is the gradient of this guy. Okay, so this guy is 2 A transpose AX. Okay, and then we have this guy and this guy and this guy. Okay, and then we also have a minus sign over here. And then what do we obtain? 2A transpose AX equals or minus this guy and this guy. A transpose B minus A transpose B. And thus, yeah, this guy is represented as this guy. Okay. I didn't expect it takes that much long, but anyways, we obtained this equation. So this equation, okay, that equation is basically our normal equation that we obtained by just applying the orthogonality with the error vector with each of our basis vector or the column vector in our column space of an A. And that is the same as this normal equation that we obtained. And then at a high level, this was obtained by just taking the derivative and then setting it as 0. So it is basically the same as this guy. Okay. So if we have this function to minimize, and then we just compute the derivative and setting it as 0. So we just did it on the vector version of an input for our function. So if our function has a vector input, and then the derivative will be computed with respect to each of our individual variables, and then setting each of them as, so that will give you this equation, set of an equation. Okay, so this kind of vector calculus or matrix calculus is, so if you are familiar with this kind of techniques or tricks, and then that will open up some new and deeper insights in case you study kind of machine learning and things like that. Yeah, machine learning and deep learning. So these kind of derivation of the partial derivatives and setting it as 0, and then that is the basic component, mathematical component for deriving or optimizing the neural net or deep learning or machine learning and so on. Okay, any questions so far? Okay, so back to this. Okay, so I forgot to mention why we call it as a normal equation. So normal means normal vector is what? Normal vector. In Korean, it is called a 법선 vector라고 부르죠. Normal vector. So normal means perpendicular. So our error vector should be perpendicular to each of our column in our matrix A. So that way, this equation is called the normal equation, because that is normal or perpendicular to each of our column vector. Any questions so far? 네.
벡터를 미분 시켜가지고 기록과 구할 때
네.
아까 증명 과정 이해가 가는데 실제로 문제 푸는 과정에서 미분했을 때 미지수가 2개 이상인데 아까처럼 1차 방정식이 아니라
네.
2차 방정식 이상만 나와도
네.
실제로 0이 되는 값을 되게 찾기가 어려워지세요.
네, 그러니까 그게 고차 연립방정식은 연립방정식인데 이제 고차 연립방정식으로 가요. 네, 그리고 고차 연립방정식을 한 방에 풀기가 좀 어려워서 그래서 저거를 사용을 해갖고 그레이디언트 디센트라고 혹시 배운 사람 있나요? 그레이디언트 디센트. 약간 그걸 해갖고 차츰 이게 가거든요. 그러니까 뭐 뉴턴 메소드 혹시 이렇게 해요. 이렇게 있잖아요. 그러면 한 점을 택해요. 그럼 여기서 이렇게 그어요. 직선을 만들어요. 접선의 슬롭이랑 저 점을 지나는 걸로 접선의 방정식 세울 수 있죠. 그러면 그때 x점을 다시 펑션에 대입을 해요. 여기가 되죠. 여기에서의 접선은 이렇게 되죠. 그러면 여기로 가네요. 여기서는 접선이 어디로 갈까요? 이렇게 되니까 또 여기로 가네요. 뭐 하여튼 저런 식으로 하면 요점에 도달해요. 이렇게 뭔가 반복적으로 하는 거. 저건 뭔가 뉴턴 메소드라고 하고, 그다음에 또 그레이디언트 디센트라는 건 좀 또 다른 이제 옵티마이제이션 메소드인데 좀 한 방에 못 구해서 차츰 이렇게 구한다. 네. Any other questions? 네.
관련 질문인데 혹시 저렇게 해가지고 뭐 하는 게 그냥 그 행렬을 역행렬 연산을 그냥 쫙 해서
일단은 역행렬이 존재한다는 말은 A라는 걸로 factor out, 그러니까 이제 앞에 이제 그 상수로 되어져 있는 매트릭스, 그러니까 1차 연립방정식은 연립방정식의 1차 연립방정식일 때는 A를 뺄 수가 있고, 그때는 뭐 저렇게 역행렬을 구하는 식으로 하고요. 지금 이야기하는 거는 AX라고 안 나타내지는 거예요. 여기 있는 요 식들이 어디 갔나? 네, 이거를 AX equals 0로 나타낼 수가 있거든요. 이거를 5를 저쪽으로 넘기고 여기는 0이 가잖아요. 그러니까 여기가 마이너스 5, 0, 그 다음엔 4, 4, 6, 4 해갖고 4, 4, 6, 4가 A가 되고, 저게 2차 혹은 고차가 되면 저렇게 AX equals B로 안 나타내져요. Any other questions? 네, 그거 이제 뭐 로컬 미니머라고 하고 또 거의 머신러닝의 이 금단의 열매를 여는 것 같은데, 하여튼 그 0이 되는 지점이 여러 개가 있을 수가 있고, 그 시작하는 점에 따라서 그게 또 다 다른 점에 도달할 수가 있거든요. 그래서 그런 게 있어요. 적당히 해요, 그걸. 네. 관심 있으면 또 머신러닝이라는 걸 나중에 또 배우면. 네. Any other question? 그러니까 이 선형일 때는 식은 이거는 하나만 나와요. 이때는. 네, 선형일 때는 하나만 나오니까 그거를. 네. Any other? Yeah. Okay. Okay, so let's cover the remaining parts. So now our vector v can be, we can understand this kind of process of from b we obtain ax hat, where x hat is the minimizer of this guy, a minus b minus ax, right? So the minimizer of this guy is x hat, and then this, we obtain this, right? And then this b is now represented as two parts of ax hat plus this other part. So this is our z part, right? So that is our like a perpendicular vector, orthogonal vector. Okay, in this case, this guy can be considered as the orthogonal projection onto the column space of an A, and then this guy is our other term. So that is corresponding to the orthogonal projection and the orthogonal decomposition theorem. So AX hat, so B was decomposed into two parts, where the first part is belonging to column space of an A, and then this part. So this part is belonging to the column space of a perpendicular orthogonal complement, right? Because that part was orthogonal to any vector in our column space of an A. So it can be viewed as orthogonal decomposition. Okay, and then the solution. I mean, this orthogonal projection, so we studied that in this theorem, orthogonal projection is always uniquely defined. So that means this part, okay? This part is uniquely defined, right? So there is no multiple orthogonal projections. We only have one orthogonal projection, so that's corresponding to the uniqueness problem. And in terms of an existence, so that is uniquely defined, right? So that is uniquely defined, okay? So AX hat, or geometrically, like this point itself is uniquely defined, right? But what if, is that the same as X hat being uniquely defined? So what I mean by that is, in the column space or this plane, the orthogonal projection is a unique point, but X hat, okay? So given the A1 and maybe A2, and then X hat is corresponding to the linear combination coefficient associated with each of these basis vector to obtain this guy, right? So when is X hat uniquely defined? So that's when the columns of an A are linearly independent, right? What if we have linearly dependent columns like A3? So in that case, again, orthogonal projection point is uniquely defined, but the linear combination of that unique point will be defined with the multiple different linear combination coefficient. Okay. Okay. So in that case, so if we have a linearly dependent columns in our matrix A, and then our least square solution of x vector is not unique at all, right? In that case, our x vector for our least square solution can be multiple, right? Because we have many different ways to represent B hat as a linear combination of these redundant basis vectors, right? So that is when this guy A transpose A is not invariable. So even though the time is up, let me give just 5 more minutes. Okay. Sorry for being, sorry about that, but let me give another 5 minutes to finish this chapter. Okay, so so you can apply this normal equations in this equation, and then this one is probably the last part. Okay. So whether our least square solution is uniquely defined or not is basically the same as the columns of an A are linearly independent. Okay, linearly independent. And then I want to prove this guy when the columns of an A is linearly independent, and then A transpose A is invariable. And these are necessary and sufficient condition, equivalent condition. Okay. So I want to briefly prove that. So A is invariable, and then A is a linearly independent columns, and then A transpose A is invariable. So let's just form this homogeneous linear system, and then if we satisfy this, and then if we have a linearly independent columns, and then it will have only the trivial solution, right? If it has a trivial solution, and then if we can show this guy is also having a trivial solution, and then we can prove this guy is leading to this, and then if this guy is a trivial solution which is corresponding to this guy is invariable, right? And then this part will be will be true, and then if we show the both directions, and then these two are equivalent, which means if A is a linearly independent columns, and then A transpose A is invariable, and this one is invariable, and then this guy is also true. Okay, so if this one is holding true, and then we can just simply multiply this guy. Okay, and then this one will be 0, and then we obtain this. And so if this guy is satisfied for a particular x, and then this one is automatically satisfied, right? So if this guy has only the trivial solution, and that trivial solution will be also obtained in this case, right? So basically the solution set of this first homogeneous linear system and then the second homogeneous linear system, the solution set are equivalent. So that's what we want to prove it. And so if this one is satisfied and this one is also satisfied. But what about this one being satisfied and this one? And then this one, A transpose AX, and then if it is 0, and then let's just multiply X transpose on the left. And then this one is X transpose and the 0 vector, and then this one will still be 0. And this guy is represented as AX norm squared, because this whole part can be written as AX transpose, the same vector transpose and the vector, and then that will be this guy, and then this one will be this, and then when is is this vector having a zero norm? That's when this vector itself is just a zero vector. So again, the norm of a vector is zero, and then that vector itself should be just a zero vector. And so we obtained this guy. So at a high level, although it was quick, but if the solution, a particular x value is satisfying that, and then that will automatically satisfy that. And the solution that satisfies that, and then that solution will also be the solution of this guy. So that way we proved these solutions are equivalent. And thus, if A is linearly independent columns, and then A transpose A is invertible, and then that is also guarantees the opposite direction. Okay, so A having linearly independent columns, and then that is equivalent to A transpose A is invertible. Okay. And then let me just have just one more minute. Okay. So let's relate it as a QR decomposition. So A has the QR factorization in this manner, and then this guy, our least square solution can be efficiently or conveniently represented as this. Okay, and then we can prove it by just plugging this into this vector x part, and then A is a QR, and this one is solution. And then if we multiply it, R inverse will be cancelled out, and then we will obtain this, right? Okay. And then this guy is what? This guy is orthogonal projection. When we are given the orthonormal basis vector of our same column space of an A, right? And so this AX head, that representation is basically a orthogonal projection of the given point B onto the column space of an A, given when the orthonormal bases are provided. Okay, that's it for today's lecture. So, and this is the last class of our semester. So, thank you very much for your hard work, and please keep up with the good work, and come up with the good scores in the last final exam. Okay, thank you very much.